Hi, I'm Alisha Vira, and I am a PhD candidate in physics at Georgia Tech, working with Professor Philip First and Professor Zhigang Zhang. Today, I'll be talking about the role of near-surface vesicles in lunar water formation. So how do we form water? Water is a vital resource. From lunar orbital missions, we know that there is a large water signal on the moon, but we don't know how this is formed. On the surface of the moon, we have galactic cosmic rays, solar wind, and micrometeorites continuously bombarding the lunar regolith. Solar wind and micrometeorites are thought to play a role in water formation. The solar wind, we know, implants the lunar soil, the top 200 nanometers of the lunar soil, with these protons that can then be used to form our water. We think that the protons can be bonding with the oxygen natively found in the lunar soil to form water. However, the contribution of the solar wind implantation is also affected by the frequency of the micrometeorite impacts. So these different mechanisms of water formation are all subjects of ongoing research, and we're only focusing on one of these possible mechanisms. Last year, Catherine Burgess and collaborators found that there are these near-surface vesicles within the top 100 nanometers of the lunar soil from a returned Apollo 17 sample that contain these hydrogen-bearing species, such as H2. And they find H2 to have an internal pressure inside these vesicles of around 4 megapascals at room temperature. Now, there could also be other species of OH and H2O, because this has yet to be confirmed inside these vesicles. These vesicles could be providing us with a place for internal surface chemistry to occur. And this would occur deeper in the material, which could then be later released by solar wind sputtering or micrometeorite impacts. Our goal is to investigate these near-surface vesicles and see if it provides us with a place to promote water formation and storage. We plan to address this question by doing laboratory solar wind exposures, where we plan to implant a mineral with deuterium ions that allows us to figure out the difference between the implanted ions and the native hydrogen within the mineral. We expose minerals to around 2 keV deuterium ions at a fluence equivalent to 1,000 lunar years, which is roughly the time for turnover, lunar soil turnover. And we look at lunar analogs because we want to look at a simpler system, such as the individual lunar analogs that make up our complex lunar rock. So one of the analogs that we look at is anorthite, but there's others like albite or olivine that we can look at. Before looking at the lunar analogs, we want to calibrate our deuterium source so we understand the damage, the amount of damage that it has on materials that we have well understood, like silicon wafers with a silicon oxide on top. So we implant these materials and we want to investigate these near surface changes. To look at the changes in the surface topography, we use atomic force microscopy, AFM. AFM is particularly difficult to use on a surface that has a lot of surface topography, such as a rock or a mineral. So we want to look at flat surfaces like wafers, so we can easily distinguish the damage due to the ion implantation. For the minerals, we want to look at the subsurface damage, where we can do lift out a 5-micron cross-section from a mineral and use a focused ion beam to do this, or FIB. And this will create a sample that we can image in the TEM and SEM, where we send 200 keV electrons through this. So before looking at the minerals, let's look at our calibration material, SiO2. So here we see an unexposed AFM image, and we see the surface fluctuations are roughly 0.4 nanometers. Upon exposing it to deuterium ions at a low fluence, we see that we create these spatially separated blisters that can contain our implanted deuterium gas. And these blisters go up to a height of 3 nanometers. Upon increasing our fluence, these blisters start to merge into one another, making it hard for us to spatially separate these blisters. And then when we further increase our fluence, we see that these blisters actually erupt, forming these deep cavities down to 50 nanometers. So here we have an REU student, Pranav Rain from Haverford College, who implemented a machine learning program to measure the percentage of blister coverage. Here we show the blister coverage as a function of fluence, where we can see these two domains. At the low fluence, we have spatially separated blisters, and then we have an erupted blisters regime. Our goal is to expose anorthite and perform a fib lift-out to image these near-surface vesicle formation. And a fib lift-out is a standard technique that's used in TEM. So this is just a brief description of what we're doing for a fib lift-out. So here we have an SEM image, and the slice in the middle is what we're going to lift out. What we've already done is we've milled out a trench in front and behind of the cross-section that we want to lift out. Then we're going to use the focused ion beam and mill out around this trench to isolate it. And bring in our needle that will weld to this lift out sample, lift it out from the material, and then take it over to our grid where we mount it to the grid, remove it from the needle, and then polish it down to a thickness of approximately 40 nanometers so we can get a transmission of electrons. So we did this for anorthite before any deuterium radiation so we can establish our baseline. Here we can see in the black, we can see that there is a vacuum, and then we can see our carbon protective layer, which is what we put on in order to further protect the interface that we're interested in. Then we can see our gold coating that we put on for the, so that we have conductivity. And then we have our anorthite. The anorthite that we're looking at is very inhomogeneous, and it has these native pores in it that makes it very porous. Upon exposing it to deuterium ions at a fluence in the first column, we can see a fluence that's equivalent to spatially separated blisters in SiO2. We amorphize approximately the top 400 nanometers of the anorthite, and then it transitions to a crystalline material, which you can see by the birefringence pattern in the TEM imaging. Then we can expose it to a regime where we had the spatially erupted blisters and see what that subsurface damage looks like. Upon doing that, we see that we create these huge voids on the scale of 100 nanometers. And these voids are saturated up until the top 250 nanometers of this surface. There's still a lot of data to fill in between. What happens between this amorphous region to a saturation of voids? Do we have some small vesicles within our amorphous regions that's close to the scale that we were seeing in the Apollo 17 samples? The overall question that we're trying to answer is, do these near-surface vesicles promote water formation and storage? We've calibrated our deuterium source using SiO2, exposed anorthite to 2 fluence regimes. What we plan to do next is look at other mineral analogs, such as albite and olivine. And we plan to expose it to a regime where we have these spatially separated vesicles, both on the surface where we have these spatially separated blisters and subsurface. Then we plan to perform nano FTIR to do a chemical species identification over these vesicles. With that, I would like to acknowledge everyone who has made this project possible. Thank you.
I think we can take one question. Anyone has one?
I got a quick one. I'm just wondering, what was the flux you were using?
The flux that we're using is for the spatially separated vesicles was around 10 to the 17, and for the erupted blisters around 10 to the 19.
No, but
Oh, the flux,
beam current.
the beam current was spatially separated 50 nanoamps. And then the one where we had the erupted blisters was 1 microamp. Your typical exposure for 1 microamp for 9.5 hours.
Okay, thanks.